Hello everyone, I welcome you all to Startup Academy, India's exclusive coaching for ISS examination. In the previous lecture, we did Central Limit Theorem, which was the last theorem or which was the last mode of convergence. And in that, we discussed what do we mean by Central Limit Theorem and some of the important properties of it and the further derivation or the direct results that could be used in that Central Limit Theorem. So basically, I'll be revising Central Limit Theorem today with some of the questions or your PYQs that has been asked previously in the ISS examination. So what does Central Limit Theorem mean? Central Limit Theorem said that if we have random variables, suppose we have xi x1, x2 up till xn, n random variable, sequence of random variable that are IID, independent and identically distributed, and that had mean, finite mean, and finite variances. These four were the conditions. Independent, identical, mean is finite, and variance is finite. That means they exist. So if these four conditions are satisfied, then we can say that Sn, which is nothing but summation of all these random variables, all these xi's, Sn will follow normal distribution. Sn in law will converge to normal distribution. This was our central limit theorem, as I've told you earlier. And the statistics that was used was Zn, which is nothing but Sn minus expectation of Sn upon under root of variance of Sn. And this Zn always follows normal distribution, or we can say standard normal distribution. This was all about the things, and the properties all are included in the previous lecture. So if you haven't seen that video, you can go back to that video, then rewatch it, because we'll be discussing question, and if you are unknown of the facts about the theorems, then you won't be able to get these questions. So let us start with our first question. The first question of today has been asked in ISS examination 2019. Here, in the first question, they have given us the round off error of the second decimal place has the uniform distribution on the interval disk. Suppose xi's denote the round off error to the second decimal. So xi follows IID uniform with the limits minus 0.05 and 0.05. This has been provided to us. So first of all, let us calculate expectation of xi. Expectation of xi is nothing but, because it follows uniform distribution, it will be a plus b upon 2. So it will be 0.05 minus 0.05 plus 0.05 upon 2. Minus plus will get cancelled and we'll be getting 0 as our answer. So expectation of xi is 0. When we calculate variance of xi, it is nothing but b minus a whole square upon 12. B is the second limit, which is this, and this is the first limit. So b minus a. 0.05 minus minus will get plus 0.05. This will be 0.1 whole square upon 2 upon 12. And when we solve this, we'll be getting 1 upon 1200 as our variance. So we have calculated xi, the expectation of xi, which is mean, and the variance of xi. Now what have they asked? They have asked us what is the probability that the absolute error in the sum of the 1000 number is less than 2. So these xi, I goes from 1 to 1000. The last nth term we have got. And what do we have to calculate? We have to calculate the probability. Suppose we are denoting it by small p. Probability that modulus of Sn, which is the absolute error in the sum, the absolute error in the sum is less than 2. So we have to get this probability. How do we calculate? First of all, we'll see what is Sn. Sn is nothing but summation of I goes from 1 to 1000 xi's. Now we have to calculate expectation of Sn. Expectation of Sn is nothing but expectation of this term. Summation I goes from 1 to 1000 xi. And since expectation can be taken inside, it will be summation I goes from 1 to 1000 expectation of xi. And expectation of xi from here can be written as 0. So summing it over 1 to 1000 will always give us 0. Now we have to calculate what is the variance of Sn. If we are calculating variance of Sn, it is nothing but variance of summation I goes from 1 to n xi. So variance can be taken inside just as we did in expectation. 1 to 1000 variance of xi. Now variance of xi here is 1 upon 1200. So I'm directly writing it 1 upon 1200. Since there is no I, so the sum will be 1000. So this will be nothing but 1000 upon 1200, which will give us 5 by 6. So we have got expectation and variance. Now we have to calculate the uh, Zn, and this is also Zn. Now we have to calculate Zn. How do we calculate Zn? Zn is nothing but Sn minus expectation of Sn upon under root of variance of Sn. If we calculate this, Sn can be written as Sn only, minus expectation of Sn is 0 upon under root of 5 by 6. Okay, so this is Sn only. Now let us see how do we calculate this. So we have to calculate that probability Sn is less than 2. If we have to calculate this, then we will be calculating P is equals to probability modulus of Sn is less than 2. Now Sn upon root 1 by root 2. If we divide both the side by root 5 by 6, 2 upon root 5 by 6, it will become on moving upwards it will become root 6 by 5, and 6 by 5 is nothing but 1.2, so it will become root 1.2. So it will be probability that instead of Sn upon root 5 by 6, I can write Zn because it is equal to this. So Zn is less than 2 into 1 root 1.2. If we calculate this, we'll be getting 2.19. So this is our probability that Zn is less than 2.19. Now this probability can be termed as that probability. If we are calculating that Zn is less than equal to a, then this will be 2 into phi a minus 1. This is our normal table. From normal table we calculate this. So it is nothing but probability that Zn is less than equal to 2.9. I can write it at 2 into phi 2.19 minus 1. Now phi 2.19, they have given us that it is equals to 0.985. So 2 into 0.985 minus 1. So it is 1.97 minus 1, which gives us our answer as 0.97, which is our option number C. And hence our option number C is the correct answer. So here we have used CLT, the central limit theorem, by using this statistic. This is how we use central limit theorem in a question. Now moving forward to the second question. Let us see this one. So in here, they have given us that xn is a sequence of IID random variables. They have given us expectation of xi, which is equals to 1. This is xi, not 1. I1, because all are identical, we can take it as expectation of I. And variance of xi or 1 is less than infinity. So both the, it is also less than infinity, mean is also less than infinity, and variance is also less than infinity. And they have given us that it is IID, this random variables. So all the conditions of CLT are fulfilled. Now they have given us that x1 square and all these minus 1 reaches to normal 0 1. So from here we can say that x1 square plus x2 square up till xn square upon minus 5n upon root 12n follows normal distribution, standard normal distribution. So we can say that xi square follows summation of xi I goes from 1 to n, xi square follows normal distribution with mean. See here, if we have taken here as summation I goes from 1 to n, xi square minus expectation of xi square upon variance of xi square, right? So it will follow normal with mean 5n and variance 12n. From this, we can denote this. And now they have asked us to calculate variance of xi. We know the formula, variance of x1 or xi is equals to expectation of xi square minus expectation of xi whole square, right? Now expectation of xi square, from here we can calculate expectation of xi square, which is nothing but 5n. So it will be 5n minus expectation of xi square. So xi square, expectation of xi is 1. So 1n. If we are calculating for i's, if we have to calculate for 1, instead of n we will put 1. So it will be 5 minus 1, which will be equal to 4. So variance of x1 is equals to 4. And option number A is the correct one. This was your PYQ from 2021. Now moving forward to another question. Here in this question, they have given us that suppose xi's are independent IID random variables with finite second moment. Second moment is variance, so it is finite. And for some x belongs to real number. Then they have told us to calculate the probability. They have given us that probability summation of xi. So I am taking summation of xi as Sn. Sn is less than equal to x root n will converge to phi 2. They have given this. Now for this and the variance of common distribution is this, and they have given us that the variance of xi is equals to 4. They have given us these two terms. So first of all we have to calculate zi. So for zi it will be Zn is equals to Sn minus expectation of Sn upon under root of variance of Sn, right? First of all we have to calculate this. So Sn, they have given us, let us take it as Sn only. Let us do it in this one. So probability that Sn minus expectation. So let us assume here that expectation of xi is equals to 0, because they haven't given to us, and without that we can't conclude. So we are assuming that xi is equals to expectation of xi is equals to 0. So we are taking minus 0 upon is less than equal to x root n minus 0 upon variance Sn. So upon, if we are taking that variance of Sn, variance of xi is 4. Then variance of Sn is equals to summation I goes from 1 to n 4, which will be equal to 4n. So here we will be putting 4n under root of 4n. We are dividing here 4n under root. It converges to phi 2. They have given this to us. Okay. Now from here we can say that probability that Zn, because this is nothing but Zn only. So Zn is less than equal to x root n upon 2. So instead of this we can write root n get cancelled, and root 4 outside root will be 2. So x upon 2 converges to phi 2. Now if Zn is less than equals to x by 2, then this also converges to phi x by 2, and we have been given this value, x by 2 is equals to 2. So if we put x by 2 is equals to 2, we get the value of x as 4. From here we have got our value of x as 4. Okay. Now we have to calculate for this one, the variance. Then we have to calculate for this probability that this is equals to. So they have given us probability that Sn is less than equal to 1 by n, 1 by x root n. We have to calculate what does it converges to. So first of all we have to calculate convert Sn to Zn. So Sn upon 2 root n we have to divide is equals to 1 upon x root n upon 2 root n, right? Root n get cancelled, and we'll be getting probability that Zn is less than equal to 1 upon 2x. But from here x is 4, so instead of x we can write it as 4. So 2 into 4 will be 8. So this will converge to phi 1 by 8, which is your answer. This equals to phi 1 by 8. So we have used here CLT only. Everywhere we are using CLT. These are CLT questions, and this was your ISS 2021 PYQ. Now moving forward to another question of CLT only. This is also 2021 PYQ. Here they have asked that they have given us that xn are the sequence IID randomly distributed mean. So they have given us expectation of xi is equals to 1 by 2 and the probability of the event for infinitely many n. So they have asked us the probability of this event. They have asked us probability that modulus of xn is greater than n by 2. Infinitely for many n means limit n reaches to infinity. Okay, so they have given us this. Let us consider that variance of xi is nothing but sigma square. Now we can take this limit n tends to infinity, probability we can write it as 1 minus probability that modulus of xn is less than equals to n by 2. Let us take this. So limit n tends to infinity, 1 minus probability xn lies between minus n by 2 and n by 2. Let us consider this. Now xn minus expectation of we have to calculate by CLT. Limit n tends to infinity, 1 minus probability minus n by 2 is less than equals to xn is less than equals to n by 2. So we have to calculate first of all expectation of xi. So it will be minus half. So it will be minus half here and it will be minus half here upon under root of variance, which is sigma upon sigma upon sigma. So this will become minus n plus 1 upon 2 sigma, and this will become n minus 1 upon 2 sigma. So instead of xn minus half, we can write zn. So this will become our probability. Now when we put the limit here, when n reaches to infinity, it will be minus infinity, and when n reaches to infinity, it will also be infinity. Okay, now here we can say that Zn, which is nothing but xn minus expectation of xn upon under root of variance of xn, will always follow standard normal distribution. So the value of xn will always lies between minus infinity to infinity. The probability that it will lie between minus infinity to infinity is surely 1. So instead of this probability, we can write it as it is nothing but 1. And 1 minus 1 will give us 0. So our option number A is correct, which is equals to 0. This is how you solve by using CLT theorem. Now the last one, this question. In this question, they have given us Bernoulli trials for a sequence of Bernoulli trials. In 2021, there were a lot of questions that has been asked from the same topic. So this is very important topic. So if X follow Xi, IID follows Bernoulli distribution with with parameters p and is a consistent estimator. So if we calculate expectation of xi, it will be np, and if we calculate variance of xi, it will be npq. Q is nothing but 1 minus p, and they have asked us about the fraction of success. So if we are calculating expectation of this fraction, which is x upon n, it will be p here, and if we are calculating variance of x upon n, it will be p q upon n. Okay, now they have asked from which of the following theorems or inequalities or the convergence theorems we can prove that it is the consistent estimator of probability. So here we will calculate probability that xn is less than epsilon is greater than equal to is less than epsilon is greater than equal to variance of x by n upon epsilon whole square. And this is nothing but our Chebyshev's inequality. How have we used this? If we use probability that x by n is less than epsilon and variance of x by n is nothing but pq upon x epsilon square. And if we put limit here, limit n tends to infinity. If we put limit here, so 1 upon n, 1 upon infinity will become 0. So pq upon n epsilon square limit n tends to infinity will become 0. So it is 0 with the probability equals to 1. So Chebyshev's inequality says that xn in probability will always converge to p when xn is nothing but the Bernoulli sequence of x is nothing but the sequence of Bernoulli trial, and it is always a consistent estimator of our probability p. So here we have used Chebyshev inequality and not central limit theorems, de Morvay Laplace theorem or law of large numbers. So this was all for today's lecture. I hope the CLT, the central limit theorem, is clear with all of you. And if not, then you can ask us in the comment section or on our WhatsApp channel. Only relevant doubts will be answered. All the best. Thank you.